Alaikum assalamullahi ta'ala. Welcome everyone. I'm your host Zaman. Welcome to School of Physics with Zaman Quantum. I'm your host at my YouTube handle Zaman Physics. So this series is about the quantum mechanics, and this is quantum mechanics series. Well, this is the outline of what I'll be teaching. I will be your teacher, your tutor, whatever you may call it. And in this series I will be covering all of these topics which are here. These are all the important topics which will be covered under the category, under the series of quantum mechanics. First and foremost, I apologize if I do any mistakes in my English because my native language is not English, so kindly forgive me for that if I speak anything wrong, pronounce anything badly. So I apologize for that on the first stage. So coming to our topic, we are dealing with quantum mechanics. So first and foremost, I will clear this very thing that since quantum mechanics is advanced topic, is advanced subject in the field of physics. So why I have taken that? There is only one reason, and the biggest one, even though there is a lot of stuff available, but not as compared to other fields like classical mechanics and other things, the subject is not that much available on social media platforms. So I have taken this so that my students will be given a bit of thought about the quantum mechanics to make the basis for the advanced physics. Okay, so coming to our topic here, we'll be dealing with we'll start from basics, go to the medium level quantum mechanics, and then to the advanced level quantum mechanics. Okay, for that we will first deal with few topics where we will discuss the failures of the classical mechanics, okay, and those will be the certain kind of experiments which were done by the scientists and the people in the 19th century, late 19th century and the 20th century, and these will include the topics like black body radiation, photoelectric effect, the Compton effect. In fact, those are the topics and those are the experiments which were done, and these blow classical mechanics apart. Okay, it was thought that the classical mechanics is the final theory in the physics, but when these things were experiments were done on these very things, there was something missing. Okay, so people thought that there is need of some other field, there is need of some other subject, there is need of some other theory which is beyond the classical mechanics, and that gave the birth to the quantum mechanics. Okay, so in this subject, in this series, in this quantum mechanics series, we will be dealing with the black body radiations, where we will be studying in depth what does this black body mean and how they radiate. What does a black body do when photons, or we can say, well, energy is absorbed by it, whether it is radiated or it is absorbed totally. We will see in detail about those very radiations. In this topic we will be covering like Venus displacement theory and Stephan's theory. In fact, Stephan's law, where Stephan derived the equation where he said that the energy density is directly proportional to the fourth power of the temperature of that very body. We will see that in details, which was the basic foundation for the quantum mechanics. And furthermore, there are other laws were given in this field also, like Planck's radiation law. We will be dealing with that also. Furthermore, the photoelectric effect, there were certain experiments done on this field where the radiations were studied under different conditions, and it was in the 1905 Einstein who well explained the photoelectric effect on the basis of the particle nature of the photons, the particle nature of the light, which in classical mechanics earlier was thought that the photons, that the light is made up of waves. These are waves, but in 1905 Einstein said that no, there is a particle nature inside the photons as well, inside the light as well. So we will be dealing with this photoelectric effect, the nature of that, the nature of the photons, the nature of the light. Furthermore, other experiment was done by Compton. We'll be dealing with that also, where they deduced the particle nature of light, the particle nature. So we'll be dealing with that. These will be dealt very much in very much depth, so that these two are the experimenters, these three rather, are those experimenters which laid the foundation of the quantum mechanics. And then, not the least one, the de Broglie hypothesis, or hypothesis, whatever you may pronounce it. So de Broglie gave the theory based on these very theories, the photoelectric effect. He said if there is a particle nature found inside the photons, then de Broglie said that nature allows symmetry. In the physics, there you will always see that there is a symmetry, an overall symmetry. Even though in some fields you might see the asymmetry is also there, but overall the nature allows symmetry. So he said that if the nature is lovable to symmetry, then there must be reverse of that also. That is, if photons or if light is behaving as particles, light as a wave is behaving as particle, then there must be a wave nature in the particles as well. So for the sake of argument, he took the example of the electron. He said that electron is a particle, but there is simultaneously a wave associated with it. We'll be dealing with that. That's the hypothesis of de Broglie. And in fact, we'll be dealing with the other thing, which is Heisenberg's uncertainty principle, that if there is an uncertainty inside the particle, inside the momentum of the particle p, which is represented by delta p, and it is uncertainty in the position is delta x, then their multiple is always greater or equal to h bar by 2. This is his theory. Similarly with the energy and time also, if there is a certain kind of, he said that there is always a certain kind of uncertainty between these relations, between the energy and time. There's always uncertainty between the momentum and position of the particle. There's always uncertainty associated with this, and that very is called as the Heisenberg's uncertainty principle. We will be dealing with that also. So in this field, this is very, very much interesting. You will enjoy this field. Coming back, there was a scientist known as Schrödinger, very much renowned scientist in the field of quantum mechanics. He gave the theory called as the Schrödinger wave theory. He said that with every particle in the quantum mechanics, there is always a wave equation or a wave form or a wave function associated with that particle, which is generally represented as psi. This is the wave function which is associated with any particle in the quantum mechanics. And furthermore, he deduced the various kinds of equations, like he deduced equations for the probability inside the, how we can find the position, how we can find the energy density of those very particles which are under discussion, and the probability is this psi star psi. So we will talk about those very things in detail. And he laid the foundation of this wave theory of quantum mechanics. Okay. Furthermore, then we will be talking about the electron spin, what is the behavior of electron inside an atom, inside a particle box, when we place a particle inside the box. For example, this is what I will write. So for example, this is a box. We'll be taking inside it a particle and see what is the behavior of this. As the Schrödinger said that with every particle there is always the association of a wave functions psi with it, and we will be seeing the probability density, how it is behaving inside the potential well, what is the behavior of the particle when we place this in front of a potential barrier. So all kind of stuff will be discussed under this, and ultimately we'll be dealing with the electron spin, and we'll be dealing with these kind of concepts, and furthermore the Pauli's exclusion principle for a specific particle, especially in this case a fermion. If an energy level is occupied by a particle, a fermion, then there is no possibility that other electron, which is a fermion, can overtake this until and unless this is removed from it. Okay, so that means a specific energy level can always be occupied by one fermion only. So that is, all other particles are excluded. So this is the Pauli's exclusion principle. We will be dealing with that with the passage of time, and which will lead us to the structure of atom, how an atom actually works. This is all about this very theory, which will come under the Schrödinger wave theory. Advanced topics like coupling inside the atom, how is the behavior of the electron inside the atom. For example, this is an atom, this is a nucleus, and around this nucleus the electron is revolving around it, and it will be inside a orbit. What will be the nature of this orbit? What will be the nature of this orbital inside which the particle electron is present? And there will be always a kind of coupling between the spin which is exhibited by the electron and the orbital motion. So what is the nature of that very coupling? We will be dealing with those very phenomena, which are a bit advanced topics, but that will be very much simplified with the passage of time. We'll be dealing with the LS coupling, which is the spin and angular momentum coupling. Then total angular momentum will be dealt in detail, and what is the nature of that very angular momentum, how does that coupling takes place inside an atom or inside the system, which will be under discussion. And furthermore, in this field we will advance to the topic called as the Zaman effect. This is, to some extent, this is related to my name also here. Okay, so we'll be dealing with that Zaman effect also. What is the nature of those very processes, those very effects? What are these effects? What happens if a particle undergoes such an effect? What is the anomalous behavior of that very electron or that very particle which is under discussion? We'll be dealing with all the such stuff. Then, in fact, the quantization of the energy, because in the quantum mechanics the particle inside a system always exhibits kind of energy levels which are quantized. That means the energy exhibited by the particles is not continuous. There is always some discrete level of energies which is exhibited by the particle, by the system. We'll be dealing with those kind of quantization of the energy, and which will ultimately result in the understanding of the true nature of the atom. We'll be dealing with the rotational energy quantization, future projects, like we'll be dealing with the advanced quantum mechanics and the nuclear physics, which will be derived from these very concepts. Okay, so our future projects will be the advanced quantum mechanics, wherein we will be dealing with the time-independent stuff, time-independent Schrödinger wave theories, because here we will be dealing only with the time-dependent here will be dealt the wave theory which will be time-independent stuff. Furthermore, we'll be dealing with the time-dependent stuff also. So advanced quantum mechanics will be dealt in detail, even though sometimes it might be seen that the stuff goes on a bit boring, but we will try to avoid those very things. We will try to make the things simpler. Okay, so that's all for today, the outline of quantum mechanics with your host Zaman. So kindly stay with us for this series. I will see you in the next. Thank you.